Welcome to lecture 6 of organic chemistry. And in the beginning, we will again start with a short revision of last lecture. Last time, we introduced the aromatic compounds, and we also talked about the special stability and reactivity of benzene. And we learned that there is a general rule which determines aromatic and anti-aromatic compounds and also non-aromatic compounds. The Hücke rule defines a compound as aromatic if it is cyclic, planar, so that means it only contains sp2 hybridized carbon atoms, and it contains an uninterrupted ring of pi electrons. And hereby, the number of pi electrons is 4 times n plus 2, whereby n can be 0, 1, 2, 3, and so on. Conversely, a compound is anti-aromatic if it is cyclic, again planar, and it contains also an uninterrupted ring of pi electrons, but this time the amount of pi electrons is 4 times n. And furthermore, we learned that aromatic compounds do not necessarily have to be neutral, but they can also be charged or even contain heteroatoms. And if we want to describe or if we want to explain the special stability and reactivity of aromatic compounds, we learned that it is helpful to have a look on the molecular orbitals. And here it is helpful to use the Frost circle. For benzene, we saw that special stability is ascribed to the delocalization of 6 pi electrons, and the structure of benzene is a planar hexagon with bond lengths between the carbon-carbon single and the carbon-carbon double bonds. And here is the Frost circle for benzene. So we know that this overall structure is a hexagon. That means we start with drawing this hexagon in that way that we have one vertex pointing down. Afterwards, we draw the circle around this hexagon, and each intersection between hexagon and circle can be then assigned to a molecular orbital. Then we draw a line through the midpoint of this hexagon, and we describe all orbitals which are below this line as bonding molecular orbitals, and all orbitals which are above this line are described as anti-bonding molecular orbitals. And then in the last step, we fill up the molecular orbitals with the numbers of pi electrons, and we know that for benzene we have 6 pi electrons, so we fill up each molecular orbital with 2 electrons, whereby the orientation of both electrons has to be in the opposite direction. And then finally we see that we only have filled bonding molecular orbitals, and the anti-bonding molecular orbitals are completely empty. And this fact then explains why benzene is so stable. And of course, the Frost circle can also be drawn for other compounds, for example, for cyclobutadiene, which is an anti-aromatic compound. And similar to benzene, we draw again first the overall structure of cyclobutadiene, which is now a square. Then afterwards, we draw the circle around the structure, and each intersection between square and circle represents then one molecular orbital. Here we see, after pointing the line through the midpoint of this square, we see that we now have 2 molecular orbitals exactly on this midpoint line, and these molecular orbitals are called non-bonding molecular orbitals. And after filling the orbitals with electrons, we see that we end up with one completely filled bonding molecular orbital, and additionally with 2 half-filled non-bonding orbitals. That means for cyclobutadiene, we have 2 unpaired electrons in the system. And here we can see already the difference. Benzene is very stable. Conversely, cyclobutadiene tends to react very fast in order to pair these 2 unpaired electrons. And finally, the Hücke rule also describes what is a non-aromatic compound, and here the compound should be cyclic, non-planar, and contains either an interrupted or uninterrupted ring of pi electrons with the total number of 4 times n. That was it for the revision from last lecture, and now we will continue with the reactivity of benzene. And as we learned last time, benzene has a special reactivity and stability, and also benzene has carbon-carbon double bonds. It does not react similar to an alkene. So it does not undergo electrophilic addition reactions as you might maybe expect, but the electron-rich ring of the benzene molecule does react with strong electrophiles in so-called substitution reactions. And this is a very big difference. So also we have the carbon-carbon double bonds in the benzene molecule. We do not see addition reactions, but instead we see substitution reactions with benzene. What is now an electrophilic substitution reaction? Very general, we can say that in an electrophilic substitution reaction, an atom or a group replaces a hydrogen atom on the benzene ring so that the product contains then the stable aromatic ring and one substituent. And it is very important that we see what is the reason behind this special reactivity. And very shortly, we can see that in case benzene would react like normal alkene, then we would have an electrophilic addition reaction. And that would mean that we end up with such a product. So we have the electrophile as well as the nucleophile, the end product attached to the benzene ring. And you can already see that would mean that the final product is no longer aromatic. So we have here then 4 remaining carbon atoms as sp2 hybridized, but on the carbon atom where the electrophile is now attached and the nucleophile would be sp3 hybridized. And that means the aromaticity of benzene would be broken. And this already explains why benzene does not react in this way, but instead with electrophilic substitution reactions. And here we can see we started with benzene molecule and we end up with another aromatic compound which looks exactly like benzene, but now we end up with no longer a hydrogen atom being attached to the benzene ring, but an electrophile. So in other words, the electrophile just substitutes the hydrogen atom. And here the advantage is that we retain the aromaticity of benzene. And the reaction mechanism for the electrophilic substitution reaction is a 2-step mechanism. In the first step, which is the slower step, 2 electrons of the aromatic ring, which is the nucleophile, are attracted towards the electrophile, and hereby the aromaticity is broken as a new carbon electrophile bond is formed, which lead to a non-aromatic carbocation. And this first step can be seen here. So we start with the benzene molecule and we have an electrophile next to it. Then we will see that one of the carbon-carbon double bonds attracts towards the electrophile, and then we go into the first transition state where we already have the new carbon electrophile bond partially formed, which is indicated by the dotted lines. At that moment, you can draw also inside the benzene ring this dotted half circle, which indicates that the positive charge is now delocalized around the ring. And then we go from the first transition state into the intermediate, which is a non-aromatic carbocation. And here you can see that the new carbon electrophile bond is already formed. That means we now have to draw the positive charge inside the molecule. And now we have not only the pi electron density delocalized around this benzene ring, but also the positive charge. But be careful, here on this carbon atom where we have now the electrophile attached, the pi electron density is not delocalized. That means you have to stop the dotted line before this carbon atom. The reason for this is that you can directly see this carbon atom is no longer sp2 hybridized, but now sp3 hybridized. And this carbocation is also called arenium ion. And also, the arenium ion is not aromatic. It is stabilized by 3 resonance forms. Then we continue and go into the second transition state where the carbon-hydrogen bond is already partially broken. This you indicate again by this dotted line. And then the partially positive charge is again delocalized around the ring. And then in the second step, the faster step, the carbocation, so the arenium ion, loses a proton, which is usually during the reaction with a base. Then the 2 electrons of this carbon-hydrogen bond will move inside the ring in order to regain the aromaticity of the benzene ring. And what is important here is that you see that the deprotonation will always take place from that carbon atom, which forms the new bond to the electrophile. And overall, the electrophilic substitution of benzene produces a substituted benzene molecule where we now have one hydrogen atom replaced with an electrophile. From the energy profile of the reaction, you can see that this first step, the generation of the first transition state where we break the aromaticity, has a high Gibbs energy, but then at the end, overall Gibbs energy shows a negative value. That means the formed products are energetically favored. To sum it up, due to its special stability, benzene undergoes electrophilic substitution reaction and not electrophilic addition reactions. And the 5 most common electrophilic substitution reactions of benzene are the halogenation, nitration, sulfonation, alkylation, and acylation, which we will discuss in the following slides.